Motion tracking has been an important technique in physics-based motion synthesis. In this work, we focus on addressing the challenge of motion tracking with rich interbody contacts and perturbations, using the large-scale open-source interhuman dataset. Motion tracking involving frequent contacts is very different from those simulated in single-character environment because the tracking model is required to handle the inconsistent forces from the opponent. Existing motion tracking methods are typically trained in contact-free environments, which limits their ability to adapt to dense interactive contacts. Some studies address two-character competitive motions, but they are either restricted to specific skills or require costly training of high-level controllers, making them difficult to scale to large-scale interactions. We propose an all-in-one progressive learning model capable of handling complex interactions and producing stable actions across multiple expert policies. We design a mechanism that enables the gating network of the mixture of experts model to predict independent confidence scores for each expert given the input samples, and to compute the proportion of samples routed to each expert. Specifically, earlier experts are encouraged to handle samples with higher confidence, while later experts focus on predicting complementary offsets for more challenging samples. At inference stage, we simply reuse the gating network to select the expert with the highest confidence as the final output. Here, we first present the motion tracking with boxing interaction, where the green markers are the target positions to simulate and the red markers are contact points between the two characters. MLP and MOE suffer from different levels of catastrophic forgetting, while our method produces more accurate and stable tracking. Here's another example. PNM performs better than other baselines, but still struggles to handle contact. Our method also succeeds in transitioning between different interaction skills, whereas other baselines are prone to failure. This demonstrates the robustness of our model in learning complex tracking patterns. We further evaluate tracking performance under object perturbations. Our method maintains stability in most cases, even when heavy objects are thrown at the characters from different directions. Compared with the baselines, our method also achieves a higher success rate under perturbations. Here, we inject random noise with various scales to the input and test how robust the model is. When noise scale is up to 0.7, the model starts failing and produces unstable actions. Compared with the baselines, our model demonstrates greater resilience to noisy inputs, whereas PNN tends to overfit to specific subsets of motions and fails quickly. Here, we show how the experts contribute to the final outcome by predicting complementary offset actions. With only one or two experts, the characters often fail to maintain stability. Adding more experts improves performance, with the third and fourth experts yielding comparable results.